Okay, good morning to our in-person and virtual audience here from Egypt at the COP27. It's my great pleasure to welcome you here at this joint IAEA WMO side event on supporting member states in reducing their greenhouse gas emissions. This event will basically showcase how the application of stable isotopes can be used to measure the release of greenhouse gas emissions and therefore to accurately determine their source, so where they're coming from. This can be an excellent, and one can even argue invaluable tool to generate that knowledge and scientific evidence that is needed so that policymakers that are also here can effectively implement those measures that reduce their greenhouse gas emissions. It's my pleasure to introduce you to the panel, to our three panelists today. My dear colleague Katharina Defra, who is an IAEA Program Management Officer in the Department of Technical Cooperation. We have Ms. Oksana Tarasova, who is from the WMO and the head of the Global Atmospheric Watch Network. And we have Ms. Celeste Saulu, who is the first Vice President of WMO and the head of the Argentinian National Meteorological Center. You will be hearing a presentation from these three panelists now, and then later on we'll open up for questions from the audience that you might have. Thank you very much, and Katharina, the floor is yours.
Thank you, Christoph. And a good morning to everyone. Good morning to everyone, and I welcome you to this session. As Christoph already said, we are actually here on a matter that is quite pertinent to all the member states, and to add on to the previous panel, we are hoping to actually give some valuable tools to member states to translate the science into action. So we are here to talk about a project that we are implementing in joint cooperation with the WMO. And again, for those who haven't heard, I think my microphone just went up. It is the purpose of this presentation is to introduce to you the work that we do in translating the science into very applicable tools for member states to help them reduce their greenhouse gases, to provide them with the tools necessary to reduce greenhouse gases. So I'm gonna start with a little introduction on, and I would like to see the slide if I may, please. Could I see? Yes. So I was struggling a little bit on whether I should talk about the IAEA since we are here, but quite frankly, over the past days, there's been so many people who still ask, why are we here? Why are we at all at COP27? And it is indeed the first time we have a pavilion here. But the reason we are here is that the IAEA, despite what we are known for, has to offer a lot to the world when it comes to addressing the problems that climate change has introduced to the world. So I want to talk a little bit about who we are and then why exactly we are here, pertinent to the project that I just referred to. Next. Oh, I'm sorry. I have actually the option to do this. So, really quickly, we have currently about 173 member states, and 2,500 people are working for the IAEA. We have headquarters in Vienna, and laboratories in Cybersdorf in Monaco, and regional offices in Toronto and Tokyo, and of course the liaison offices that we have in Geneva and in New York. I apologize for my voice, by the way. These are, here you see a little bit of the breakup of the organization, and you see safeguards, which is what we are actually known for mostly as the nuclear watchdog of the world. But today I'm here to actually talk about the work that we do in the Department of Nuclear Science and Application. And we'll focus on that. The IAEA also does work in nuclear energy and in nuclear safety and security. I'm here representing the Technical Cooperation Department. And the Technical Cooperation Department is the entity of the IAEA that transfers the knowledge and the know-how of the agency to the member states. So we are the bridge connecting what has been, or the competencies that the IAEA has to offer to our member states. So these are the areas that the IAEA actually functions in. So it's quite wide, and you see there is health and nutrition, there is industrial application, radiation, environmental and water, and of course energy. And as already mentioned, the focus of the work that we are talking about right now is primarily in the area of environment. So, why are we here? Again, the IAEA has to offer quite a bit when it comes to addressing the aspects of climate change and the challenges that the member states are facing. We work with clean energy, that is what we are offering, climate smart agriculture, water management, and also we work with the reduction of greenhouse gases, or producing tools to help member states to reduce greenhouse gases. And that is where we are narrowing down now to what we are trying to do here. And that is help member states who committed under the Kyoto Protocol, under the Paris Climate Agreement, under the SDG, to meet certain goals and to have certain commitments. And in order for them to do and meet these commitments, they need to have the tools on how to actually do that. So these are the questions that most of these member states are asking themselves. Where are the emissions coming from? How are we going to reduce them? How much can we in fact reduce? So this is a challenge that the world is indeed facing, and it is scientifically quite challenging to answer these questions precisely. So we work with the WMO, the World Meteorological Organization, together to actually provide the tools necessary. And I would like to start showing a video that gives a little bit of background first before we continue here. So may I please ask to start the video?
How can we fight climate change if we don't know where greenhouse gases are really coming from? Governments around the world are making serious commitments to reduce their national emissions. But to do that effectively, decision makers need to know the exact amounts and origins of the different gases being released in their region. A cutting-edge scientific technique is now giving governments and industries this data. Scientists are using something called stable isotopes to fingerprint each gas present in a sample of air and trace its source. This allows the authorities to target their climate policies to the biggest polluters and not miss any problem areas. Such indisputable data reveals the reality of emission sources and helps authorities build local support for focused climate action. The International Atomic Energy Agency is working with the World Meteorological Organization to help countries perform these measurements and generate the data needed. The IAEA and the WMO are setting up regional centers to analyze the data received and teach scientists how to apply this technique in their home countries. Because the air in each country will tell a different story, and we can't solve a problem that we don't understand. How can we fight climate?
Thank you very much. So we missed a little bit in the beginning, but it is exactly what we're going to go into depth with this topic anyhow right now, but the question is really how are we able to determine the source of greenhouse gases? And I would like to start with an example. There has been a member state who was facing a tremendous amount of methane emissions. And it was a country that is very agriculturally heavy. So they presumed that the methane is coming from cows, from crops that they had, quite a lot of. And an analysis was actually done, and it turned out that it wasn't the cows, it was industries. So in order to reduce, and they changed some kind of processes in the industry and were able to significantly reduce methane emissions. But what that goes to show is that you need to know on where a greenhouse gas comes from in order to take effective and meaningful action and not do something that might actually not have an effect. So it's quite an important tool to have. And for this we have the project. This is the title. And I'm not going to repeat it. Again, it goes to the source attribution, helping the member states to identify the source of a specific greenhouse gas. Now, why the IAEA? The IAEA is the custodian of reference materials. So again, for those of you who might not know what that actually means, is we have in Paris, there is reference material for a kilogram. So in order to actually measure something properly, you need to have reference materials, and the IAEA produce reference materials for greenhouse gases. So we are the entity that the rest of the world will actually look to for verification of their measurements. The WMO has a global atmospheric watch network that connects the member states in their reporting of greenhouse gases. So it turned out that there are areas in the world that are quite bleak in their competencies to actually report on greenhouse gases. So you have Africa, you have Latin America, and you have Asia, who are not really able to measure yet greenhouse gases accurately. So as a result, these are the areas that we are trying to focus on with the project. And I would like to hand it over right now, first to my colleague Oksana, to give some of the technical backgrounds on how stable isotope measurements can support climate policy. Oksana, please.
Thank you, Katja. It's a pleasure for me to be here, and I will deep dive in the technical details. What are the stable isotopes and why do we actually need to measure them, and what kind of additional information they bring to us. First of all, let's just refer to why do we measure greenhouse gases at all? Well, these are the drivers of climate change, and if you look at our increase of the main greenhouse gases in the atmosphere, carbon dioxide, methane, nitrous oxide, they are the main drivers of climate change, and due to their presence in the atmosphere, we increased the warming in the atmosphere since 1990 by 47%. And if we look at the temperature increase in comparison with pre-industrial, we are already at 1.1 degree temperature increase. So if we wanted to tackle the problem of climate change, we do need to address greenhouse gases. And the need for information to be used in the mitigation of greenhouse gases is actually embedded in the Paris Agreement itself, but basically it boils down to the need to know the baseline, so where we are now. We need to know the geographical and sectoral distribution of emissions, where do they come from. We also need to understand the response in atmospheric concentration, because it's the concentration in the atmosphere, it's what you have in the atmosphere which actually drives the climate change. to the mitigation action. So if you do something, does it make sense? Does it actually end up in the atmosphere in one way or the other? But also because many of the greenhouse gases, including the main ones, CO2, methane, and N2O, they have both anthropogenic and natural sources. You would like to know what happens with these gases in the future. Like if you have a warmer temperature and then you have an immense emissions of methane coming from the wetlands. So that would impact your mitigation trajectory. So you want to come prepared, and you need to understand where does this come from to address it. So if we look at the value of atmospheric observation, I just put on the screen one example where under Montreal Protocol, the emissions of the ozone-depleting substances, which are also greenhouse gases, are controlled. So it's about the production and consumption of the ozone-depleting substances. So we have a long-term data set of observations in the atmosphere of those gases, and then we look at how fast it decreases in the atmosphere, because there should not be new sources. And then at a certain point, when we look at the atmospheric observation, they do not decrease as fast as they are supposed to do. So we look at these observations and we track them back. And what you can see on the plot is actually in 2007, you have new sources of emissions of the substances which are forbidden under Montreal Protocol. So we use atmospheric observation to actually find out if our commitments and if our measures are working or not. And indeed, those measurements allowed us to understand that there are new sources of the CFC11. Those sources were identified, and as you can see on the plot, the emissions dropped after the paper was published on those new unexpected sources of CFC in the atmosphere. So that's why we have the Global Observing Network within the World Meteorological Organization, which actually looks at the changes of main greenhouse gases. And this network is coordinated by the Global Atmosphere Watch program, and it works since 1989. And we produce long-term data sets of global averages of greenhouse gases. These data are openly available. WMO implements open data policy, so everybody can go in a World Data Center, download the data, and do the analysis themselves. All those data are traceable to primary standard and have a very high quality. Unfortunately, when we look at the map which you have on the screen, we have massive gaps in the observational network, which oftentimes don't catch the changes in the source areas of those gases. And also, the global averages data are not very useful if it comes to decision making. Like, who's responsible for global average? Which country is responsible for global? Is it industry? Who can actually change it? So we need to get a better granularity. So how do we, in general, estimate the emissions? So we estimate the emissions using the bottom up, which is a national inventory, and that is following the protocols established by IPCC. Highly standardized, very much are clean and very much agreed method how we do it. But it's based on the self-reporting. Like, I collect the activity data, multiply by emission factors, and this is what I report. It gives you national total annual. Also not super helpful if you wanted to address particular sectors. Or we can use atmospheric observation, as we've done in the case of CFC11, and we call it top-down. Like, we look in the atmosphere, we analyze atmospheric observation, do the analysis, and then we get to the emissions. Where do they come from? And if we do the combination of the traditional reporting, the bottom-up, and the top-down, we get the most comprehensive knowledge on emissions, their distribution, and we can get it much faster. If you measure in the atmosphere, you see what is happening. Atmosphere tells you what is happening. But then you need to do the attribution, because what you see is a total. So let me give you an example. This is a plot which is coming from our colleagues in New Zealand, and they use observations of CO2, and they use the thing which is called carbon-14, which is a radiocarbon isotope in the CO2. And they use it to attribute the uptake or emissions of CO2 in the country. Because if you have fossil fuel, then there is no radiocarbon in fossil fuel. So when you burn the fossil fuel, you reduce the amount of radiocarbon in the atmosphere. So it's proportional to the signal in the emissions. So what they've seen is that when they use atmospheric observations of CO2 and carbon-14, and they've done the attribution of these uptakes to the land use land cover sector, from the observations which are in green, you can see that the uptake is actually much larger than reported. And this is really great, yeah? So the uptake is much better. But you can also see a lot of variability. It's not the same every year. You have more precipitation, you have more uptake. You have less precipitation, you have less uptake. The precipitation and temperature are not part of the emission factors. You can't do it with a traditional inventory. And also what you see on the plot is that the uptake happens in a particular area where they have the old grown indigenous forest and not where they have a new plantations. So you can ask yourself, if you go and do the reforestation project, would it have an impact if you don't make the measurements to confirm if it works or not? So, and here you understand why we need to use the isotopes. So isotopes is a different form of the same molecule, where you have one of the atoms inside the molecule which has a different weight, the atomic weight. It just has additional neutron in that atom. So we can have, for example, traditional CO2, where you have the carbon normally has a weight of 12, but then you have when you have the atom which has a weight of 13 or 14, and it's mixed with the CO2, so we can use it and we can measure that to do the following things. So we can do the information on sources, because different sources of greenhouse gases produce different isotopic composition. So they can have more carbon-13, less carbon-13. They can have more oxygen, 17 or 18, and the same. So that gives us the good information about the sources, but also it defines what is the sink process for those gases, because it changes this isotopic composition of the gases as well. And we can also trace the atmospheric transport, deposition, and the loss in the stratosphere. So how we do it, we measure the concentration of the gas, and we measure this delta value, which reflects the isotopic composition, and then we have the regression model, which indicates us what is the signature of the source. And as you've seen in the video, each source has its particular fingerprint, which we can identify with the measurements. So this plot shows you the difference in isotopic composition for methane. You can see that the biomass burning has very low delta 13 in methane, and the methane natural sources like tropical wetlands, ruminants, and the boreal wetlands, they are very light in carbon 13 because those are driven by the biogenic sources and the microbial processes. And you can see here for the changes in the isotopic composition of N2O, where you look at a different molecule of our nitrogen molecule and oxygen molecule, also identifies different sources, sinks, and the transport processes. So how do we use it? We use the isotopic composition to understand the recent increase in methane. So there was an increase in global methane since 2007. And if we look at the isotopic signature of that methane, which is in the lower plot, you can see that as long as the concentration started rising dramatically, so it was rising pretty slow, but then it started like kicking off, then you can see that methane, we call it, gets lighter. So there is less and less carbon-13 molecule in methane. And usually this is associated with the microbial processes, because microbes are very selective. They don't like heavy food, they like light food, so when they eat organic material, they produce normal methane with carbon-12 and very little of carbon-13 in the production, microbial production. But at the same time, we struggle to identify where it comes from, because there are indications that it comes from the tropical areas where you have tropical wetlands, where you have rice paddies, where you have waste and ruminants. And unfortunately, they are all microbial and have pretty similar isotopic composition. So we need to set up and extend our observational network to really drill down in those areas. And this is where we hope our cooperation with IAEA will be useful to actually build up the capacity to make such measurements. The same radiocarbon is very useful to identify the fossil fuel component in CO2. So if you look at the plot, the carbon-14 signal is proportional to what you see as a CO2 fossil fuel. So we do have a very strong cooperation with IAEA, and we started our cooperation in 1997 because the IAEA is a custodian agency for the primary isotopic standards. And within the project, which Katya already mentioned, we will build the capacity for making isotopic measurements in the atmosphere in the parts of the world where those measurements are not available. But also to help the traceability, IAEA started developing new reference materials which will help us to actually compare apples with apples. So we need to compare each sample which we collect with a primary material to make sure that all the countries produce similar data and we can put them all together. So they produce new reference materials for CO2 and for their isotopic composition, as you can see on this slide. And there is a lot of innovation which is going on in the production of these reference materials. There is a new kind of a carrier where you can put this reference material or reference gas, which is the tubes, the Klaus tubes. You don't need a lot of reference material, unlike the big flasks where you have to have a dilution. So you can use this small container and then connect it with a bigger flask, have a dilution and get the reference standard. So this is a stability of the standard. You can see that within the period where they were tested up to 1 month, there is a very high stability of the standard and those tubes, and then you connect it with a cylinder with the clean gas, and you can get your isotopic reference material, which you can use to calibrate your instruments. So the plan for this is to get the feasibility study for methane in the same tubes and prepare the materials and test them in the lab. There are at least 2 labs that already confirmed the stability of those standards, and there will be the intercomparison with the other labs are under the ISO standard. Yeah, so we have this example of this. Thank you so much. So this is the reference material. Well, it's not the tube itself, it's what is in the tube. That is important. The answer is in the air. It's there in the tube. Thank you so much. And that will be used then to calibrate all the globe so that everything can be compared together. And I think with that, I will pass it back to Katya.
Thank you very much, Oksana. This is for you to have somewhat of a technical background on how this actually works and how or what we are trying to achieve, and the work that lies in front of us. I would, before I move on to some of the concrete examples of what the project is trying to achieve and where we are right now, I would like to pass it on to Celeste for a couple words in her work with the WMO as the first vice president. And then later on, I would like to draw on your expertise once more when we talk about the Argentinian National Meteorological Center. Please, Celeste, to you.
Thank you very much, Katia. Thank you, you all, for being here. And after the context provided by Katia and after the master class presented by Oksana, which I enjoyed really very, very much, I think that you, because it's natural, who is behind this? That's the question. Who will do this? How we can share expertise and work to do these measurements and to share these measurements. And here is where the WMO comes with the work of Oksana and the Global Atmospheric Watch. That is science that is coordinated around the world. But I think that presumably you were also struck by the map shown by Oksana, the huge gaps around the world to make these measurements. And that's why the WMO coordinates the measurements, provides the knowledge, and tries to diminish this huge gap between the countries around the world. So who is behind the World Meteorological Organization, which is based in Geneva, that has colleagues like Oksana with high expertise, or has colleagues like me being the vice president? Behind this, the member states do have weather services, national meteorological and hydrological services. These are the real crucial actors to perform these measurements and sustain these measurements during as much as possible. No? You can, we are here at COP, you know, we are at COP 27 speaking about climate change. Who started the measurements of temperature for us to know that the climate is changing? The National Meteorological and Hydrological Services. We can speak about 1.1 degree above industrial over pre-industrial era because we have weather services doing this. In particular, my weather service this year has celebrated 150 years old. That's why we are speaking about climate change, because we could perform these measurements. And now the challenge is to go for these more complex and expensive kind of measurements. And when it comes to infrastructure, science, and knowledge, and ways in doing complex measurements, we have to help the less developed countries to do that. And so that's why I'm here supporting this project, this huge impact project, because I think that we need, as it was very clearly stated by Katia and Oksana, that we must measure to perform adequate mitigation and adaptation efforts. It is not the same for Africa, it is not the same for Latin America, it is not the same for Europe. The measurements are different, the signals are different, the atmosphere responses in a different way, and the plans for mitigation and adaptation have to be coordinated and have to be related to this science and measurements. So thank you very much for this opportunity. I will go back again to the example of Argentina in a few moments, but as WMO, I think it's very important to take care about the importance of measurements and keeping the measurements for this long time period. Thank you very much.
Thank you very much, Celeste. And to add on to this, and it really drives it down, and I'm very grateful that you make that strong point, because what we have heard so much, and we have in the previous panel also discussed the fact that the science is there. We all know about it, but the key is to translate that science into action. And as tried as it sounds, that is very much where the challenge lies. Everyone wants to reduce greenhouse gases. Everyone wants to go and proclaim that they did reduce greenhouse gases, but how exactly do you do this? And that is where that project for the development or the more developing world comes in, because you have countries like the US and Canada, and of course Europe and New Zealand and Australia. They are all able to do this. This is very complex science. It requires quite a bit of costly equipment, but there are these gaps. As you saw in Oksana's presentation, there are big holes in reporting, and that is in Africa, in Latin America, and in Asia. So how are these countries, though the majority of the countries that are residing in these three areas are part of the Kyoto Protocol, are part of the Paris Agreement, but how are they actually going to achieve that goal? What can they meaningfully report? So you have a whole bunch of politicians who would like to report on things, but again, these politicians need to rely on the scientists to provide the tools, and that's where the project comes in, because we are trying to provide the scientists with the tools to reliably identify the source of a greenhouse gas in their country, report it to the WMO, so that there is a means to have an reliable, intercomparable data set available to make an educated assessment on where we are on climate change, where we are on the emissions. Are we indeed reducing them or not? So let me get back to the project that we are implementing here. And again, I apologize for my voice. But there are some very concrete aims that are hands-on, that are aimed to be hands-on, that we are trying to achieve in the frame of this project. So we are trying to establish regional training centers. And as we already pointed out, we have these three areas that are quite bleak in their competency to report these greenhouse gas emissions. We are starting with one training center, and I get into detail with this, in Argentina, serving the Latin American region. We're also looking at Africa, and we're looking at Asia. We will produce and develop good practice documents, meaning how do you actually do sample taking. It's a guide, a very simple hands-on guide. How do you take the samples? How do you analyze them? How do you interpret them? We are training trainers in order for these regions to become self-sufficient eventually and actually train themselves. We are developing standard operating procedures and quality assurance and quality control systems and programs. And we will organize regional workshops and training courses to kickstart these training efforts in the respective regions. So these are the aims of the project itself. Again, the project is a global project, and it will go on for quite a while in order to achieve these very concrete and hands-on, but of course very complex and large-scale goals. Now, the project has been going on for a little bit, and I would like to report on three of the major achievements that we have reached so far. That is one, that we established the first regional training center, training and analysis center in Buenos Aires, in Argentina. And here Celeste is of course heading that center amongst her other functions. But another one, so this is a big step. We are equipping the center and we are training the trainers there. We have already the first draft of a good practice document for methane sampling analysis and interpretation. And we have started to train the trainers. Again, we're talking here about the Latin American region. Here I would like to actually draw on Celeste once more. You see here is the Regional Training and Analysis Center that we are hoping to further develop and set up at the Meteorological Center in Buenos Aires. Here is a picture of it. And again, Argentina is a very advanced country in the sense that they did indeed translate their commitments into their national aims. And with that, actually, I would like to have you talk more about this. Celeste, thank you.
Thank you very much, Katia. Now I'm changing my hat from Vice President of the WMO to the Director of the Weather Service in Argentina. Thank you for the nice photos of our building there. And well, I think that WMO has a particular strength, and that is building capacity. And in that capacity building activity, Argentina has a role for South America and for all the Spanish-speaking countries in Latin America, going from Mexico, Caribbean, and of course South America. So I think that we were chosen because of this strength also, and because our government has a strong commitment with climate change measures to fight against climate change, and particular, more than a commitment, we have a law. We have a law that states what are we going to do to mitigate and adapt to climate change, and so to achieve the goals that we are having as a country. Of course, achieving neutral carbon, being neutral by 2050. And in this law, we have included this particular project. So I think that here it comes to the issue of governance and how you reach the higher level of politics to make them understand that this is important, and linking laws with practices, with science, and with international organizations. This seems to be easy, but it is not easy at all. It is not easy at all. So we have WMO playing, IAEA playing, my weather service, and all my staff working with, and the high-level policy decision is there. So that's why Argentina has the possibility to contribute, to start being the trainers for the region, and we are very excited about this. Next week, our expert on these issues will be going to Vienna to start her training, and then we will start to build a network throughout Latin America, which is one of the regions with, as shown before by Oksana, has less measurements in the world. So thank you for this opportunity, all our commitment to the success of this project. Thank you very much.
Thank you, Celeste, very much. So as Celeste already said, Argentina is indeed spearheading that effort in Latin America, and the country itself, namely, put their action where their mouth is. They actually translated their commitments that they made under the COP25, I believe that was, into law, into the associated budgets with it. So Argentina is committed, and as such really provides an example to the rest of Latin America on how to move forward. So we as the agency and the WMO are quite pleased to be able to actually work with Argentina and Celeste's team to provide this type of example. But not only that, because it is the first regional training and analysis center, Argentina is also serving as a pilot to the rest of the world. So when we are going to other regions, we will be looking to Argentina as the first of such centers that will be then established. I would like to also say a couple words to the good practice document. The good practice document on methane is a very, as I said already, hands-on tool for technicians, scientists around the world on how to properly take a sample, how to properly analyze it, and how to properly interpret it. And it is very important, such things don't exist yet, it is very important to have something like this in place for the scientists around the world to have one common go-to tool and document, again, in order to produce data that is intercomparable. So we're not just talking about the reference materials that need to be used in order to calibrate equipment, but you also want to have the same kind of methods applied, that there is in harmony across in how things are done. For that purpose, for the good practice document, we actually gathered the heads of the world, if you will, in the scientific field to work on that document. So these are the leading scientists from the US, in INSTAR, NIVA, New Zealand, EMPA, which is in Switzerland, and the University of Heidelberg in Germany. These are experts together with IAEA experts from Cyberstorf and from the WMO, Oksana and her colleagues, to actually sit there and devise that document. We're hoping to have the document ready for peer review by the beginning of next year. The first draft has been completed, so that is very exciting, and we will publish it as an IAEA document in the course of next year, and it will be available then. Now, when we look at what we're doing now, again, the setup of a training center is underway. We bought relevant equipment, and we are in the process of training trainers. Celeste already mentioned it. We are organizing 2 training courses, in fact, next week, one in Cyberstorf and the other one will be Cyberstorf Vienna, in order to have one of the trainers getting trained and becoming a trainer herself. So the first step of this type of efforts is underway. Again, it will pave the way for more trainers to be trained. Now, having told you a little bit about what we have done so far and where we're at, I would also like to let you know a little bit on where we are going, because again, we have quite a bit in front of us. And the next step will be to find another area to develop. We are right now looking into Africa or Asia, and we will establish a second training and analysis center there that will serve the region, similar to what Argentina is doing right now for Latin America. And we will then proceed with training trainers there, holding workshops, etc. We are also hoping, right now, you heard what Oksana was mentioning, we are focusing on methane, the greenhouse gas methane right now, to provide competencies to analyze and interpret methane. We will move into carbon dioxide later on. So that is the second big goal that the project is aiming at. So that is basically the setup of the project right now. I would like to now open it up for questions and answers. It was a lot of information. I hope it wasn't too much. But yeah, I would like to open it up for questions and answers now. Thank you very much.
Thank you so much. Mike?
Please.
Thank you. No. Hello? Yeah. Thank you very much for this excellent and interesting presentation. You mentioned you have a question, no? I have also a couple of questions. Go ahead.
Yes, thank you very much. I'm also very impressed what is going on. I had no idea that the IAEA was doing that in cooperation with the World Meteorological Organization. I would just like to know who is measuring the methane emissions from the how do you say that? From the permafrost that is vanishing. You know, I heard there's a lot of methane emissions. So who is doing that, and what's the basis for that, and how reliable is the data?
Actually, the polar regions is one of the other gaps which we have in the observing network. There are a couple of the laboratories which are measuring. There are laboratories in the stations in Finland. There is laboratory in Norway. There is the observatory in Russian Federation in Tixi. And there are several in Canada which are measuring over the permafrost. And some of them are doing isotopic measurements, but majority don't. But we have some reference measurements there. But the area is not densely covered with the observations. So it's one of the areas which we're trying to address as well. And we will be talking about the gaps and how to extend the observing network later on today at the greenhouse gas event and the WMO pavilion. But indeed, in 2017, when we saw the increase in the methane growth rate, it was pretty stable for about 10 years, and then it started growing. The first idea was it was a melting of the permafrost in the polar regions. We looked at the observations, and 2007 was pretty warm summer, and measurements at summit actually showed pretty high jump during that year, but that was just one summer. So then it turned out that it's biogenic, but it's largely driven by the tropics, and it was just an anomaly in 2007. So it seems it is not driving the increase in the growth rate, but as I said, the observing network is so poor that given everybody talking about methane and methane pledge, we as scientists cannot even reliably answer that question. This is pretty difficult situation, I should say.
Would that answer your question? Yes. Any other questions?
Yes. I have a question on the similar point on scalability, because Oksana, you mentioned in your presentation that there seems to be the possibility of quite some annual variation in emissions. So what actually needs to be done in order to be set up as regional network training centers as well as on a national level? So in terms of capacity, but also institutional capacity, staff to be trained, how many samples to be taken in order to generate a global network that is accurately measuring what you want to measure?
Yeah, thank you for this question. I think the reason why we started looking at methane is that we have instruments which allow online measurements of methane and isotopic composition in one instrument, which provides you the continuous picture of what is happening. Then there is no a universal answer. Depends how the sources are distributed in country, what are the sinks which are distributed in country. So the tailoring will be pretty specific for the country needs. And I think that on the capacity development, well, we can ask what is the capacity in the country from Celeste, and she can tell you how much efforts are needed. Mm-hmm. So how many staff do you train?
Good question. You need very specialized staff for these kind of activities. In fact, the person that is going to receive this training, she has a PhD and a postdoc level of kind of education. So imagine how important is to rely on good measurements taken by those that are well prepared. It's very expensive for countries. It's really very heavy for a developing country to really work on this. But I think that we have to, when we speak about climate action, we are speaking about also strengthening the scientific capacity of the countries to deal with climate change. So in my country, for example, we have a continuous increasing of personnel with a high level of education so that we can go into the next step. You can imagine that, just a very brief example, in my country we are 1,100, but only 25 people have a PhD. So this is the kind of thing that we have to work with. But robust measurements are key to drive good conclusions, and we have to take care about that. And I'm really worried about that, and I think that all the countries should do the same. Thank you for your question.
Thank you.
I can actually add just one more thing, and that is to simplify the process of uptake and ensure scalability. We work on a good practice. And if you look at the good practice, I mean, this is a second iteration. And I mean, when we looked at the first version of the good practice, it was like, these are scientists talking to scientists. It's not very practical what they write in the document. So we actually explained that sometimes the scientific community cannot actually deliver the knowledge to the developing countries. So they write the papers in such a convoluted and complicated way that you give up on the first page. So that's why we revised those measurement practices. And I mean, we struggled with Katya, really like checking on our relatives, checking on our children, checking on our parents. Do they understand? They are not specialized. Can they actually open the document and say, okay, take the device, put on the table, connect cable A, connect cable B, see that the reading is no higher than that, no lower than that. So it's really, sorry for the, it's translated, like, it's idiot proof thing, which we try to do. That actually what is needed. If you want to build a capacity, you don't come to the country and say, oh, there is isotopic fractionation happening in your instrument, and then you lost your audience right at that phrase. So we try really to make the knowledge available so that it's not just the people with PhD who can run the instruments, but if you come to the country where there is an issue with the general STEM education, that they can actually participate in this activity and they can be part of the solution. They can provide support to their government saying, hey guys, we are doing something which is really working.
I would also like to add actually something to that, because it is not only that we try with the good practice document actually to provide, as you so fitfully say, it's an idiot-proof guide. And I use myself as a non-technical person and my family also as a reference. Do you understand that? Someone who has absolutely no idea from the scientific point of view. And when we understood it, we knew this was what could go forward. But to even go the step further, it is not only that we're trying to actually translate highly scientific methods into easily digestible formats for lesser educated or lesser degree level staff to run these type of machineries and to actually interpret data properly. But we also, and that is I think where we bridge it to the decision makers, we are trying to actually come up with a digestible way to interpret the data and say, okay, given what we just learned, this is what you, government, Ministry of Environment, Ministry of Health, that is what you guys need to do in order to change your emissions. So we are trying to very concretely provide a tool to the member states to advise their decision makers. So it is not so much, it is not only the translation of highly scientific processes to technical staff, but also to translate back what you learn in these laboratories to politicians, because they are not technical people, they are not scientists. So you need to be able to translate what we learn to politicians in order for them to actually take meaningful actions. But Eva, you were going to say, yeah.
Actually, I wanted to ask or to suggest whether any one of you have thought of cooperating with the Comprehensive Test Ban Treaty Organization, which is maintaining a network of measuring atmospheric measurement stations around the world, I think in most countries, where they're measuring atmospheric emissions, mainly to monitor whether there have been any nuclear weapons explosive testings. But I think this would be an ideal, to my mind, an ideal area of cooperation to utilize their measurement stations for your purposes. And you have all the scientists there as well, so just a suggestion of mine.
Thank you very much.
Thank you. Do you want to answer this?
Yeah. Actually, we are looking at that potential collaboration because you have an extensive network under CTBTO, which is measuring stable isotopes of different type. They don't measure greenhouse gases, but you have a very educated personnel, and the network is much denser than the network for greenhouse gases. So we are looking at building the cooperation with that network of station, and where possible, to get them measuring greenhouse gases as well. So that's our next step.
Let me add to this. CTBTO, of course, is very much a source. There is a caveat, though, that the member states of the CTBTO, they report their data through the station under a certain agreement, and that agreement is that the data is not shared. But there are, as we are in talks to have some kind of differentiation in that very comprehensive commitment that they made. But yes, they of course have these stations, and they are much tighter knit around the globe, actually. So yes, thanks. Any other questions?
On that very interesting note, on further collaboration, utilizing existing networks to the degree possible, I must unfortunately inform you that we have reached the end of our allotted time. You see, it went very fast because it was very interesting, and I really would like to thank you all for listening in here in person, but also virtually, and I would really like to thank our three panelists for their very interesting presentation, project, collaboration, and I really personally wish you all the best of luck with the implementation of this project and all associated work, because we all know it's tremendously important. Thank you.
Thank you very much.
Thank you.